Okay, let's resume. So in the first half we were talking about simple homotopy equivalences, and I'll try to explain geometrically what simple homotopy equivalence means. And in this section I'll be talking about CW complexes, but the same holds for handle decompositions, just thinking of handles as thickened cells. So I'll just deal with the marginally easier version of CW complexes. So let me explain what the elementary operation corresponding to these elementary matrices is. So let's say if we have a finite CW complex, we'll call it X with X bar, and we say this is an elementary expansion of another finite CW complex, X, if we can write X bar as X union an n disk, where the n disk is attached in a particular way. So where the n is attached it's attached by this f, where we're attaching part of the boundary. So we take an n-1 disk in the boundary, and we attach that onto the n-1 skeleton of X in such a way that the boundary of this n-1 disk, so the boundary of F, is contained in the n-2 skeleton. So let's draw an example of this. So here n's going to be 3. Here's X. Here's some part of the 1 skeleton. And here's a cell in the 2 skeleton. And then we attach a 3 disk to this 2 cell such that the boundary is in the 1 skeleton. So this is where F is attached. We've got our 3 cell, and then this gives us X bar. So hopefully that should be clear. And this is attached around here. So if we can obtain X bar from X via an elementary expansion, we write the following. This upward pointing arrow with an E for elementary. Also, we write just this without E for elementary if we can get X bar from X via repeated elementary expansions. So if X is X0, we can expand to X1, we can expand to ... to Xn, which is X bar. And then similarly, we write this for the other relation, that if we can get X from X bar via elementary contraction. Well, what's an elementary contraction? It's the opposite of expanding. If we remove a disk that is attached in this particular way. So this is elementary contraction. And then similarly for this notation without the E, if we do several contractions and we get X at the end. And then finally we write X, and then we have this upward then downwards arrow. If we can get from X to Y via a mixture of the above, some elementary expansions, some contractions. And in this case we say that X and Y are simple homotopy equivalent. So this is what I claim is going on geometrically with the simple homotopy equivalence. I'll spend the rest of the time explaining to you why this corresponds with torsion being 0 and how to define the torsion and see that it's 0. And also a quick remark that without loss of generality, if X and Y are simple homotopy equivalent, then you can always think of it as doing all the elementary expansions first and then all the contractions. So we can then there exists a Z, say, such that X expands to Z and then contracts to Y. Now, actually, so let's define the torsion. Well, this is much the same as we've already said. We say if X and Y is a finite CW pair, such that Y includes into X as a homotopy equivalence, then we define the torsion of this pair to be the torsion of the relative chain complex of the universal covers. And this is in the Whitehead group. Z pi 1 of Y. Okay, and let me prove that X and Y being simple homotopy equivalent corresponds to having torsion 0. So X is simple homotopy equivalent to Y, rel Y, so we're not expanding or contracting anything in Y, just in X minus Y, if and only if this torsion is 0. So then this corresponds with what we said was simple homotopy equivalence before in s-cobordism theorem. So the proof in one direction is fairly straightforward, and the other direction requires a little bit more work. So to prove the left to right direction, all we require to do is show that the torsion is invariant under an elementary expansion or collapse. And then if we do lots of these, it stays invariant, and then we can collapse to Y and get, and we'll see that the torsion is 0 and doesn't change. So suffices to show that tau is invariant under elementary expansion. So if x expanded to, I'll call it x prime, rel y. So this is the situation we look at. So suppose this is the case, then we can write x prime as x union 2 additional cells. So it's union some n-1 cell and some n cell. Why is it 2 cells? Well, we've got the D3 and we've got the boundary minus f. These are the 2 new cells. So so En minus 1 was the boundary of this En minus the interior of what I called f. This was the way that En is attached. And we can choose orientations such that boundary of En is En minus 1 plus some c for c in n minus 1 relative chain. Now we already know that y includes into x as a homotopy equivalence. So this relative chain complex should be chain contractible via the lemma we had before. We know the homology is 0 and this gives us a chain contraction. And now we wish to use this to show that we can extend a chain contraction of this chain to a chain contraction of